Can you solve this crazy hard problem for one of the hardest physics competitions in the world, the Asian Physics Olympiad? I really like this problem because it considers what happens to this magnet when it drops down this copper tube. Now, if I was to drop it, it does not fall at the rate of 9.81 meters per second. And as we can see, oh right, it's only just fallen, so it's a lot slower. And we've actually talked about this in the context of Lenz's law. But let's consider what is actually happening on a mathematical level. The governing equation in this situation is mz double dot, which is the second derivative of the displacement in the vertical z direction, will be equal to the weight mg, and then there's another force which is proportional to the speed of the magnet multiplied by some coefficient. The very first problem is asking us to obtain the terminal velocity Vr of the magnet. Nice, this question starts nice and easy for half a point. To find the terminal velocity, all we need to do is set the acceleration equal to 0. So if this guy here is 0, we can write it straight away. We can say that mg will be equal to kz dot, but z dot is actually going to be the terminal velocity, so we can even call that v subscript r, giving us that v subscript r will just be mg divided by k, and we've scored half a point. Okay, next part for 1 point. 1 point usually means quite a lot of work. Let's have a look. Obtain z of t, the position of the magnet at the time t, take the initial speed, initial coordinate to be equal to 0. Oh no, I actually recognize this differential equation. If you've seen my video on looking at projectile motion with air resistance included, you will recognize this very differential equation, which is not easy to solve by any stretch of the imagination. So we're going to have to use a very similar method to obtain a function of z as a function of time. Let's do this yet again and get that 1 point. So the first thing I'm going to do is get all the z terms on one side. So we're going to get mz double dot plus kz dot. This thing here will be equal to mg. Now let's divide by m. So what we're going to get is z double dot plus k over m z dot, and this thing here will just be equal to g. We'll be solving this equation with an integrating factor, but first we're going to integrate both sides with respect to time. So what we're going to get is z dot plus k over mz. This thing here will be equal to gt plus some constant, which I'm going to call c. Okay, now look at this. Z dot plus k over m times z. We can immediately see that this here is kind of reminding us of the product rule. So what we can do is we can multiply both sides by a function f such that, shall I just write this over here? So if I was to multiply this side by f and this side by f here, and then this by f and then this by f, such that f times k over m is actually defined as the time derivative of f. And then we can use essentially the product rule to simplify this left-hand side. Let me show you. This is really cool. First of all, let's find that function f. So if we differentiate it, we get a factor of k over m times the original function. Well, that's a pretty standard one for physics. F, one possible solution, will be e to the k over m multiplied by t. Okay, we can plug that in here directly. So f z dot plus, remember, rather than f times k over m, this whole thing is equal to f dot times z is equal to fgt plus the function times that constant. Well, this whole left-hand side is actually going to be equal to the derivative of the product of fz just by the product rule, which is equal to fgt plus f times that constant. Now let's get rid of this by integrating yet again with respect to time. So if I was to integrate the left hand side with respect to t and then integrate this, pretty much all of this with respect to t, what are we going to get? The integral of the derivative is just f times z, but rather than f, I'm just going to write e to the k over m times t multiplied by z. Now on the right hand side of this integral, what are we going to get? So it will be the integral of f, which is e to the k over mt times gt, but because g is a constant, I'm just going to take that outside of the integral sign, multiply this by t. Oh no, I'm going to have to be integrating this by parts yet again in a minute. So plus the integral of f, which is e to the k over mt, times this constant dt. Okay, now let's integrate this one here using integration by parts. I was initially going to just give you magically the answer, but that's not really the way we do things here at Z Physics. So we're going to integrate this. So what are we going to get? The integral of e to the k over mt times t dt. So all we need to do is which one of those two quantities are we going to differentiate, which one are we going to integrate, and then we can use the formula for integration by parts. So I'm going to say that dv is the exponential, which is e to the k over m times t. I'm going to say that u is equal to t. Okay, well then this expression right here will be given by uv. So this expression right here will be given by u multiplied by v. So this here will be u, which is t, multiplied by v, which is the integral of this. So what is that? E to the k over mt multiplied by m over k. And then from that, we're going to take away the integral of v du. So what is that going to give me? M over k e to the k over mt, and du will just be given by dt. Okay, well this thing here will be m over k t e to the k over mt. Take away this integral here, we get another factor of m squared over k squared e to the kt divided by m. I think that's pretty much it. Let's take a factor of m over k e to the k over mt, and what are we left with? We're going to be left with t take away m over k. Okay, now I'm going to take this integral, I'm going to bring this over here and have this factor of g. So what are we going to get? Let's just do a little bit of copying. So we're going to get gm divided by k times t e to the k over m times t. Take away g yet again, m squared over k squared. And then I have another factor of e to the kt over m. Oh wait, we actually didn't write this constant of integration c2. Don't worry, I've not forgotten. I can assure you, I'll just keep you in suspense. I definitely did not forget to write this one. Okay, so let's write this as c2 plus the integral of e to the k over m times t. What is that going to give me? M over k times c multiplied by this factor k over m times t. I'm actually going to absorb this factor into this constant c, because then I'm going to just have less to write further down the line. And now I can get rid of this factor by doing some cancellations. So all I need to do is just divide this by e to the kt over m, and we are pretty much in business. So what do we get? We get that z is going to be equal to gm over k times t, take away gm squared over k squared, plus c2 e to the negative k over mt plus c. And now all we need to do is apply the boundary conditions to find our constant c2 and our constant c. First, we'll probably need to make some space on the board because this question is kind of long. Our first initial condition tells us that the time derivative at time t is equal to 0 has to be 0. So z dot of 0, which is equal, has to be equal to 0. Okay, well, the derivative of this function here will just be, what is it going to be? It'll be gm over k. When we differentiate this, this disappears. This term here is a constant with respect to time, so that just disappears. Plus c2. If we were to differentiate that, we're going to get a factor of minus k over m, and then e to the minus k over m times the time t. At t is equal to 0, though, this expression here will just turn into 1 essentially, which I'm not going to bother writing. Okay, cool. Well, this here simply means that k over mc2, what is that going to be, equal to gm over k, meaning that c2 should be equal to, oh, that rhymes, m squared divided by k squared, and we have our first constant. That is a lot of work for 1 mark. Our second boundary condition tells us that the initial coordinate, we start our coordinate system basically at the origin, so z of 0 has to be equal to 0. Okay, when z is equal to 0, this term here disappears. So what are we going to be left with? We're going to be left with minus gm over 2 over k squared plus c2. We already have an expression for c2. How cool is that? Gm squared k squared. Now, e to the minus km over t, when t is equal to 0, the exponential function is just equal to 1, so we don't have to worry about that, plus the constant c, so plus c, and this whole thing has to be equal to 0. Well, because those two are equal, look at that, this one here works out really nicely. We can find that c is actually equal to 0. In other words, our final expression for z as a function of time looks like this. Okay, let's have a look at the rest of this problem. You can tell a problem is hard when I don't film it in one take. We're given this diagram across here, and if we've switched to cylindrical coordinates, which kind of makes sense because, well, we're talking about a magnet which falls through a cylinder. We're also given that the magnet has dipole moment in the positive z direction, and we'll assume during the fall the magnetic moment remains constant, and we're also given an expression for the magnetic field in the two directions. Okay, so let the instantaneous speed of the magnet be v, obtain the magnitude of the induced EMF in the ring. Okay, well, in order to obtain the magnitude of the induced EMF, we have to use Faraday's law. Well, Faraday's law actually has a couple of forms, and this is why this competition is actually just so incredibly hard, because even knowing the second way of formulating Faraday's law is something that I've only learned at university. First of all, we all know that the induced EMF is given by the negative rate of change of magnetic flux, d phi by dt. But there's also an alternative way of formulating. Our second way of expressing the EMF when the conductor and the source of the magnetic field are moving with a speed v is actually given by the loop integral of v cross b, which will be another vector in itself that we're going to be computing in a minute, integrated over the length dl. Okay, well, how are we going to evaluate this integral? In order to do so, we need to look at those components which we have been conveniently given. We know that v has no velocity other than in the z direction, and we know that the magnetic field has a radial component and a z component. So we could just use the standard cross product rule. The first component is A2B3. Well, A2 is 0 and B3 is 0, so this guy here is 0. A3B2, well, A3 is this, B2 is 0, so our first component will just be 0. What about our second component? That's going to be A3, which is V times B1, so that's going to be V times the radial component of the magnetic field, and then take away A1, which is 0, so that's going to be it for this middle component. And finally, in the axial direction, we have A1B2. A1 is 0. Take away A2B1, which is also going to be 0. So this here will be our V cross B vector in cylindrical coordinates. And this integral here will then be equal to the speed v multiplied by the magnetic field evaluated as a radius a, because that's the radius of the ring. So what is that going to be? Mu naught divided by 4 pi, and then we're going to be multiplying that by 3 p and z multiplied the radius rho will now have a definite value, which is a, and very similarly we're going to be dividing that by a squared plus z squared and then raised to a power of 5/2. This line integral over dl, because we're moving in a full circle, will just give us a factor of the circumference, which is just going to be 2 pi a, and I think that's correct. Unless I've messed up the algebra somewhere, please do check. Okay, next part of the question. So I.4, the EMF will give rise to an induced current I in the ring. Obtain the magnitude of the instantaneous electromotive force, which is FEM on the ring in terms of I. Okay, so the formula that we're going to use, let's just consider a small element, is that a small amount of force, let's just call that dF EM, will actually just be given by the current I, and then we're going to have the cross product of B with a small element dl. This is actually the good old sort of high school F is equal to Bill equation in its true form with the cross product. Okay, now with the properties of the cross product, the z component of the field will actually just give us a force into the radial direction, but because we're dealing with a ring, this will end up cancelling itself out, because if we have a force here, force here, force here in the radial direction, the overall force is going to be 0. However, the radial component will not provide a null force. In fact, that will provide a force in the z direction, which is actually keeping or slowing the magnet down. So over an entire loop, this whole expression for the electromotive force will just be given by I, which is our current, and then it's going to be multiplied by the radial component of the magnetic field, evaluated the radius A, and then this dl component here, once it's all added up, it's just going to be the circumference of the loop, 2 pi a. And this actually makes a lot of sense. Why does it make a lot of sense? Well, the electromotive force is proportional to the strength of the magnetic field in the radial direction, and it also seems to be proportional to the radius of the loop, which also makes a lot of sense. The force on a magnet due to the ring will actually have the same magnitude, but will be in the opposite direction due to Newton's third law. Okay guys, you can have a look at the rest of the problem and let me know what you think. Now if you enjoy this problem, you absolutely need to have a look at this next one, which is one of the hardest problems to ever appear on a physics exam. Enjoy.